All right, so this week we're going to be looking at sections 4.2, 4.3. As I said, when I put up the Schoology plan, 4.2 is split into 2 days, and 4.3 is going to be 1 day. So we reviewed a little bit, talking about what happens when you make the denominator 0. And a lot of times when you make the denominator a number that it can't be, like in this case, it cannot be 2. If you look at the number 2, you get a vertical asymptote. Now, there is one exception to that. There is a time when the denominator can be a number like 2, but you don't get a vertical asymptote. You get something a little different. And let's look at something like this. Let's look at x squared plus 3x plus 2. And let's divide that by x plus 1. Okay. Now, what number are you not allowed to use for x? Yeah? Negative 1. So it's similar to the top. There's a number you can't use. It's negative 1. Well, let's graph it, and let's see what happens. So x squared plus 3x plus 2. And I'm going to divide by x plus 1. So let's watch what happens to the graph when we get close to negative 1. Let's see if it does the kind of thing it did before, where it just kind of curves down. Well, let's see. You know what? Let me do zoom 6. All right. So in that case, we get the same kind of thing. Okay, when you get close to negative 1, you get a vertical asymptote. So that's just kind of reviewing what we already did again. Is there any question why you can't plug negative 1 in for x in this case? All right. So now, let's see. Oh, okay. I did minus 2. That's fine. So I did minus 2. You plug in negative 1. You get that same vertical asymptote. Now, let me type in what I actually meant to type in, which is plus 2.
I was going to say, my graph looks a lot different.
So let me change that to a plus 2. And let's look at this one. All right, so now we got this one. And let's make another one. So x squared plus 3x minus 2. And now make it a plus 2. I meant to do plus 2 before, but you get to see another one that had the vertical asymptote. All right, so now I put in the plus 2, I hit graph, and let's see what it looks like. Okay, does this graph have that behavior where one of them curves all of a sudden? No. You still can't plug negative 1 in, because if you go to the table, second table, and you try, I got some other numbers there too, but if you try to put in negative 1, it still tells you can't do it. Because if you try to plug negative 1 in, you're going to divide by 0. But there's no way you could look at that graph and ever tell that there's a problem at negative 1. And the reason is because of this. If you factor that numerator, factors as x and x, and I have a plus sign and a plus sign. So what would my signs be in parentheses? They'd both be plus. And what would my numbers be? Yep.
2 and 1.
2 and 1. What do you notice about how we just factored the numerator and what's in the denominator? Yeah?
The denominator is a numerator. The denominator is a factor.
Factor, yes. The denominator is one of the factors in the numerator. That's kind of special when that happens. But if that does happen, then you get what's called a discontinuity. A discontinuity is basically a spot on the graph that you get an error, but you can't notice it with the calculator. To me, it just looked like a straight line. If we had to graph a problem like this last one, and we were actually graphing this on paper, what you'd want to do is this. You'd want to have a break in your line. Where would the break be? It'd be right at -1. Another name for this kind of thing is called a hole. Okay, we might have mentioned that before. I'm not sure if we mentioned it. But yeah, it's called a hole. A hole is not something you can see by looking at a graph. A vertical asymptote, definitely you can see it, because the graph curves very, very obviously. But a hole you can't see. So let's look at this one. X minus 1 divided by x minus 1. Is there a value you're not allowed to plug in for x? 1. Not because of anything that would happen in the top, but because of what would happen in the bottom. If you let x equal 1, you would divide by 0. Now, next question is, when you plug that number in, is it going to be a hole that you can't really see? Or is it going to be more like a vertical asymptote that's very obvious? Well, look at the numerator and the denominator. Is the denominator in the numerator somewhere? Yeah, just like this one. The x plus 1 was the denominator, and you had an x plus 1 in the top. Well, here, the x minus 1 is in the bottom, and that's all you have in the top, x minus 1. So what do you think is going to happen in this graph? You're going to get a hole, or are you going to get a vertical asymptote? You're going to get a hole. You're going to get a hole at the number 1. So this graph has a hole at 1. So that's really the important thing. I just want you to be able to look at something and determine whether it's a hole or an asymptote. A hole is rare. It's rare because the numerator has to be so perfect that it factors into exactly one of the things that's in the bottom. And that usually doesn't happen. But if it does, that's when you get a hole.
So is a hole the same thing as a discontinuity, or is that?
Yeah, a discontinuity is a general word for any kind of like weird thing in your graph, like a gap.
So that common factor, that x plus 1 over x plus 1 is indicative of a hole.
Of a hole, yep.
Even if that x plus 2 is still there.
Yes. Yep. Now, in this one up above, it had a vertical asymptote. A vertical asymptote is still called a discontinuity. It's a different type. Okay. A hole is a discontinuity. A vertical asymptote is a discontinuity. They're just places where you would basically, if you tried to draw it, a discontinuity means you would have to lift up your pencil, put it back down, and start again. That's a discontinuity. And it's the same thing with a hole. If you wanted to draw it, there's a gap right there, so you'd have to lift it up, put it back down, and then continue. The size of the hole is very small. It's infinitely small. Okay? There's a hole at -1. You can go as close to -1 as you want, and it's fine. But right at -1, it's a hole. So, yeah, so that's all I wanted to mention about that. Okay, so we talked about EBM a couple sections. I think it was back in chapter 3. Let's see, we had something like this. The EBM was the highest degree term in the polynomial. What's the highest degree term in that polynomial? 8x cubed. That is called the EBM. And if you remember what the EBM tells you is it controls what the graph is going to look like. For polynomials, there were 4 types of graphs. We had the up-up, we had the down-down, we had up-down, and we had down-up. People remember those 4 types? So this term alone tells you which one of the 4 types it was going to be. So the EBM is just a predictor of what the graph looks like. All these other terms control little details in the graph that we're not super interested in. All right, we're looking at like the big picture. And we had to focus on the first term and the exponent. And it had to do with whether the exponent was even or odd, and whether the number in front was positive or negative. We're not really concerned today about even and odd or positive and negative. All we're concerned about is how do you find an EBM? It's the highest degree term in the polynomial. Usually that's the first term, if it's written in the correct order. Right? But if you had something like this, that problem is exactly the same as the one I wrote below. The tricky thing is they put the highest degree term in the middle somewhere. So you want to look for that, but it's not something that you should usually write. You should always put the highest degree term first. All right, so let's say in general we had 2 polynomials. Okay? This top thing represents a polynomial, and so does the bottom. When you have an actual problem, it's going to look more like that. There's a polynomial. There's another polynomial. The way I've written it here is you start with x to a power, and then every term, that power goes down by 1. Till finally, when you get to the last thing, there isn't even an x anymore. It's just a constant. Like in this one, the constant is -1, and in this one, it's +1. So if you look at the top, this would be the highest degree term in the top. That is the term with the highest exponent. Every term after that is going down by 1. And then it would be down by 2, down by 3, down by 4, down by 5, until you finally get to the end where you don't even have x's anymore. So if we were just focusing on the numerator, that term that I put a box around would be the EBM of the numerator. This term predicts what the numerator is going to look like. All the other terms cause little twists and turns, like little details, but if we're just interested in the big picture, that term alone will tell me what's really going to happen. So that is the EBM for the top. What do you think the EBM for the bottom is? What term in the bottom is the highest degree term? Yeah.
B m x to the m.
Yeah, this one right here.
Yeah.
That's the highest degree term in the bottom. So if you want to know what the bottom would really look like, this is the only one that you have to focus on. So b sub m, x to the m, is the m behavior model for the denominator. Now, we're not really interested in what the numerator looks like or what the denominator looks like. We're interested in what the entire thing looks like. But to figure out what the entire thing looks like, that's how you do it. You figure out what the top looks like, you figure out what the bottom looks like, and then you divide the two. And that tells you what the whole thing is going to look like. Question?
I know it's just like a placeholder problem, but what is it expressing?
Those are 2 polynomials, just like that.
What are the subscripts mean?
The subscripts, that's just the so it just indicates like which term it is. So that it's just the term in the polynomial. So like if this was say an exponent of 5, then we would call this the 5th. A sub 5 would be called the 5th term. A sub 4 would be the 4th term. then a sub 3 would be the second
So
term.
just as you're going down.
Yeah.
Okay.
And then a sub 2, a sub 1, and finally your very last term is a sub 0. So it's just indicating which number term you're looking at. So like in this problem, this would be a sub 1, first term, a sub 0, last term. A sub 2, a sub 1, a sub 0. That's just the order of the terms. Okay, so we know how to find the EDM for the top. We know how to find the EDM for the bottom. And if we want to find the EBM for the whole thing, divide the two. And that'll give you your EBM for a rational function. Now, does anyone remember when you divide two things and you have a variable with the same base? Like let's say you have this. When you're dividing two letters that have the same base, like they do here, does anyone remember what you do with your exponents? Yeah? You subtract them. Well, we do exactly the same thing here. When you're dividing two things that have the same base, you're going to subtract your exponents. The a sub n and b sub n, those are just going to be two numbers. Whatever the two numbers that are in front of the x term. If we can divide them and simplify it, we will. If we can't, like let's say it was 2 over 3, we're just going to leave it as 2 over 3. If it was 2 over 4, well, that's something we can simplify to 1/2. All right, so we're going to have a lot of numbers when we do an actual problem. Now, one thing we do have to be careful about when you subtract exponents, you can end up with something that we don't want. Anybody think of a type of exponent you could end up with when you subtract two numbers that we'd like to avoid if we could? Yeah, we could get a negative. So, if you had x squared over x to the 5th, it's true that according to the formula I just gave you, you would do that. You'd take x to the 2 minus 5. And that's x to the negative 3rd. The problem is we don't want to leave a negative exponent in the answer. So if you don't remember exactly how to deal with a negative exponent, think of it this way. What does x squared mean? If you wanted to write that without an exponent of 2. Yeah?
X times X.
It means x times x. And x to the 5th, what does that mean? What do you like?
X times X times X times X times X.
Yeah. And whenever you have something at the top and the bottom that's the same when you're multiplying, you can cancel it out. We have 2 x's in the top. We have 2 x's in the bottom. We can cancel those out. Now, when you cancel out and everything is gone, what do you leave left in the top?
0.
So like if you had 2 divided by 2 and you reduce that, you'd make that a 0?
No, it'd be 1.
It'd be a 1. Yeah. So 1 over, and what's left in the bottom? X cubed. So that equals that. So the point is, when you get a number that's a negative exponent, the negative just means you have that many x's, but they're in the bottom instead of in the top. Okay, so negative means that they go in the bottom, not the top. If negatives come up. I'm not going to say negatives come up every time, but they will. All right, so let's try an example. So the directions here say to find the EBM first, and then once we find it, I'll show you how we use it to do something. All right, let's start with the top. Yep.
Alright, can I just backtrack for 1 second. That's subtracting the exponents. Why do we do that? What was that moving us for?
That's how you find the end behavior model.
Okay, so the end behavior model for that we just did would be 1 over x.
For this one is 1 over x cubed. Yep.
That's what that was stating. Okay.
Yep. You're welcome. Okay. So let's start at the top. Can anybody tell me what's the EBM of just the top? Yep.
2x
2x squared. And what's the EBM of the bottom? Yep. 3x cubed. And now we just want to simplify that as much as we can. Can I reduce 2 over 3? You think? No. So we just gotta leave that as 2/3. And how many x's? Or actually, let's think of it like this. What's going to be the exponent on my x? If we use the formula that I just showed you. Yep.
It would be -1.
It would be an x to the -1. But what does that really mean? It means we're going to have one x because it's x to the -1. But where is the x going to be? Yep.
On the bottom.
It's going to be on the bottom. That is called the end behavior model. 2 over 3x. Before we use it to find the horizontal asymptote, is there any question on how we found it? Okay, so now how do we use it? To find the horizontal asymptote, let x approach a really big value, okay, infinity. Let x approaching infinity. And then explain what's happening in your fraction. Explain what's happening in fraction. That's how you find the horizontal asymptote. So let's look at our EBM. You're going to let x get bigger and bigger and bigger and bigger and bigger. And I want to know what happens inside that box as that takes place. So look at your fraction. You have an x in the bottom. As x gets bigger and bigger and bigger and bigger, what happens to this part of my fraction? Yep.
It's larger.
It keeps getting larger. If x is 1,000,000, then the bottom is 3,000,000. If x is 1,000,000,000, then the bottom is 3,000,000,000. So the bottom is getting larger and larger and larger and larger. If you take 2 and you divide by something that's getting larger and larger and larger, what happens to your fraction? It gets smaller. It gets very small, and it gets very close to what number? 0. It's getting very, very close to 0. That is the horizontal asymptote. So as x gets bigger and bigger, you're going to take 2, and you're going to be dividing by something that's getting bigger and bigger and bigger. 2 divided by 3 billion is very, very small, and it approaches 0. It's horizontal. So does anybody remember what letter do we use when we write the equation of something that's horizontal? Yep.
Was it y?
Yep. It's y equals. And what number did we say this is getting really close to?
0.
It's getting very close to 0. That is your horizontal asymptote. That's the EBM. That's the horizontal asymptote. Now, will this, what's inside this box, will it ever actually be 0? What if you take 2 and divide by 20 billion? That's not, is that 0?
No.
How about 2 divided by 900 billion? It's still not 0. You have a 2 in the top. I don't care how big of a number you divide 2 by, it never will equal 0. Okay? It'll get closer and closer and closer to it. And that's the point of an asymptote. It's just something you get close to, but you never reach.
So wait, what's as x is approaching infinity, 0 is approaching as x is approaching infinity, y is approaching 0?
Yes.
Statement?
Yep. That's exactly it. So that means this graph is curving down towards the x-axis. That's y equals 0. That's the x-axis. It's curving down to it. So it might look something like this. I don't know the exact picture. But as you keep heading to the right, what's going to happen is it's just going to keep getting closer and closer and closer. But it's never actually going to touch it. But that's the end. And probably the same thing as you head to the left. In fact, I know it's the same thing. If you let x approach negative infinity, the same exact thing is going to happen. You're going to have 2 divided by an extremely huge negative number, which is still getting closer and closer and closer to 0. So that means the other side of my graph might do something like this. It's just going to keep getting closer and closer and closer and closer the further and further out that you go. I'm not saying this one looks exactly like that, but this is the type of graph that would have a horizontal asymptote at 0. It also has a vertical, but we're not looking at that in this problem. Let's try this one. So after you write it down, break it into pieces. Look at the top, find the EVM. Look at the bottom, find the EVM, and then divide the 2. Anyone think they know what the EVM just for the top is going to be? Max?
2x to the 4th.
Yep. And how about the bottom? Yep.
3x to the 4th.
3x to the 4th. Now we're going to reduce that by dividing our x's. And what's going to happen there? I have 4 copies of x in the top, and I have 4 copies in the bottom. Last time I had a different amount in the top and then in the bottom. This time I have the same amount. Yeah?
They cancel out to just x. X cancels entirely.
It cancels completely. This is like having x to the 4 minus 4, which is x to the 0, which means it's gone. So what do we end up with for an EVM? Yep. 2 over 3. So now I'm going to ask exactly the same question that I just asked up above to find the horizontal asymptote. We're going to look at that fraction that we just wrote down, 2 over 3. And as you look at that fraction, I want you to let x approach infinity and tell me what's happening to this fraction. Okay? So, look at that fraction. As you let the x in that fraction get bigger and bigger and bigger, what happens to that fraction? What is it? Nothing, because there is no x. So as x gets bigger and bigger and bigger, nothing happens to this fraction, which means my horizontal asymptote is at what number? 2/3. So horizontal asymptote. And what letter do we always put here?
Y.
Y for horizontal. So the horizontal asymptote is always what happens to your EVM as the x gets bigger and bigger and bigger. If there's no x, then nothing happens. It's just 2/3. Yeah.
Would there be a hole in that problem? Is the X to the fourth cancels out.
Well, we would have to look back at the original problem for that.
Yeah.
So you'd have to be able to factor this and factor that and see if there was a hole.
Okay.
Since it's a fourth degree, that's a little complicated to factor, so we're not going to look at that. But yeah.
When you talk about the x and y values, you're not talking about the numerator and the denominator, right? The x is like the variable attached to the problem, not the.
So like when I say let x approach infinity,
Yeah, you're talking about the variable and not the numerator.
yeah, I'm talking about let x approach infinity in the EDM. I'm not talking about the original problem anymore. So to find the horizontal asymptote, you let x approach infinity in the EDM, which is why it's important we get the CBM correct.
So like for that EDM, the x in the denominator is the one that's approaching infinity.
Yeah, in that case, the EDM, the x was in the denominator.
Okay.
And as far as the homework tonight, I'm going to tell you one of two things is going to happen. Either you're going to end up with an x in the denominator, or you're going to end up with all your x's canceled. You will never end up with an x in the numerator today. It's always going to be one of those two. So the first one we did, that's a horizontal line at 0. We call that the x-axis. This is a horizontal line above the x-axis. It's a horizontal line at about 0.6 repeating. Any question on how to find the EDM and then the horizontal asymptote? I think this is all stuff I was just showing you. All right, so now we're going to finish up with making a sketch. That's what we're sketching today. The degree in the numerator will always be less than or equal to the degree of the denominator. And that's exactly what I just did in the last two problems. Go back and look at the last two. The degree in the numerator was a 2. The degree in the denominator is a 3. In that case, the degree of the numerator was less than the denominator. The top was a 2, the bottom was a 3. In the one we did after that, I think they were both 4. Is that right? They were both x to the 4th. So in that case, they were equal. And those are the only ones we're going to do today. We can look at problems where the numerator is greater. That'll be tomorrow. But for today, we're going to do the numerator is less than or equal to the denominator. So these graphs are curved. So they're not as simple as just trying to draw like a straight line. It's a little bit, it's more work than that. So there's a few things we try to find that are going to help us. One thing we try to find are the intercepts. I'm not going to say that that's always going to work. Because if you look back at this graph right here, this graph doesn't have any intercepts. It never crosses the x-axis, and it never crosses the y-axis. So it's possible if you try to find the intercepts that there aren't any. So we can't just rely on finding intercepts. Finding vertical asymptotes, that's going to be very important. Most of these graphs will have at least one vertical asymptote. Some will have 2. The way you find them is you look where the denominator is 0. The only time that that wouldn't work is if you have a common factor in the top and in the bottom, then you get a hole. That would be a special case. We're going to try to focus on the case where most of the time you don't have a common factor, so you don't get a hole. So we're going to find our vertical asymptote. Then we're going to find our horizontal asymptote. Okay, well, how do you find the horizontal? That's what we just did. You find the EDM. and you let x approach infinity. Now, at this point, once we finish step 3, we've done everything that we're going to be able to do by hand. Step 4, now we need the graphing calculator. Because once you find vertical asymptotes, let's go back to this one for a second. There's a vertical asymptote. What usually happens is on one side of the vertical asymptote, it curves down. On the other side of the asymptote, it curves up. We need to figure out which side is up and which side is down. That's where the calculator is going to help us. So we're going to check out what's happening near the asymptotes. And we have to check out each side. The asymptote has a left side and a right side. Usually one side is down, the other side is up. And the way we're going to evaluate what's happening, we're going to use the table on the calculator. And I'll show you how to use the table to do that. And once you've done step 4, you should have enough information to draw your sketch. Okay, we can always double check it with the calculator to confirm that we did it correctly. But steps 1 through 4 are pretty much what you need to do. Steps 2 through 4 being very important. Step 1, if we can do it quickly, get it out of the way, and it helps us, we'll do it. If step 1 is too complicated for whatever reason, we're going to lose a little information if we don't do step 1, but we can get around. Let me show you what one of these graphs is typically going to look like, so you know what to look for. Yep.
So these steps that you just listed out, these are just the steps to like graphing in general?
These are steps for sketching the graph of a rational function. Yeah. So you're generally going to have 3 pieces. Okay? Well, you don't have to sketch this because you're going to be sketching some other ones. But let me show you what it generally is going to look like. You're usually going to end up with 2 verticals and 1 horizontal. That's going to split your area that you're drawing into 6 spaces. You usually end up sketching in 3 of them. And this is what it usually looks something like. You have a curve in that section, another curve that's trapped up in that section, and then another curve in the middle. That's pretty much what these generally look like. There's some exceptions, but that's a very common one. 3 pieces. All right, so let's try to sketch one and see if we get something kind of like that. So we're going to try to sketch x minus 1 divided by x squared minus x minus 6. One thing I would recommend doing right away is factoring the denominator. You don't have to factor it right away, but eventually you need to find the zeros of the denominator. The easiest way to do that is if it's already factored. So if we do it now, then we won't have to do it in a little bit. And it'll tell us if there's a hole in the graph. When I go to factor the bottom, what's going to be my first letter in each parenthesis? Yep, I'm going to need an X. How about my signs? Both positive, both negative, or one of each? Yep, I'm going to need one of each. Now I need 2 numbers that multiply to give me 6 and subtract to give me -1. And out of the two numbers, make the bigger one you give me the negative, because we want negative in the middle. Yep. -3 and 2. So that's a -3x and a +2x. -3 plus 2 is -1. Perfect. Okay, so now we factored it. All right, let's do the y-intercept on this problem, because that one's pretty easy. I think I'm going to skip the x-intercept, but I'll do the y. What did I say up above to find the y-intercept? What do you let equal 0? Yes, the x. Plug in 0 for the x value and find the y value. Okay, let's use the original. That's a little easier than the factored one for this. Plug in 0 for x. What's 0 minus 1? -1. 0 squared? -0? -6. -6. There's your y-intercept. When x is 0, y is 1/6. So that's like the coordinate, 0, 1/6. So it's just above the origin. That doesn't really tell me a lot. It's good. My graph is going to go through that point. But I need a little more. So now, let's find the vertical asymptotes, which are the zeros of the denominator. Okay, we haven't done it yet today, but when you write the equation of something vertical, what letter does it start with? Yep, X. And can somebody give me one number that would make the denominator 0? And I would suggest you look at the factored version. That should be a little easier. Yep. -2. And there's one other number. Yep. 3. Good. So let's put in vertical lines at -2 and +3. Okay, there's one asymptote. 1, 2, 3. Okay. Just like I said before, we're going to get those six sections. All right, so we've got the vertical asymptotes. Let's find the EBM, and then that'll give me my horizontal. Let me just make that easier to see. Okay, EBM. What's the highest degree term in the top? Yep.
X.
X. And the highest degree term in the bottom, it's not good to look at the factored one because you need to look back at the original that's all foiled out. What's the highest degree term in the bottom? Yep. X squared. And can anybody tell me what you get when you reduce x over x squared?
1 over x.
1 over x. So there's my EBM, not super important by itself, but what it is important for is the horizontal asymptote. Horizontal asymptote always starts with what letter?
Y.
Always starts with y. And now I need a number here. The number is going to be what happens to that fraction as x gets bigger and bigger and bigger and bigger. What does this fraction get closer and closer to? Yep. 0. Gets very close to 0. So there's my horizontal asymptote. I'm going to do it a different color because my axis is already black, so you won't see it. All right. Now we just have to figure out some points using the calculator, but the asymptotes kind of give you boundaries to go by. We know that on the left side and the right side of the graph, we are not going to cross the boundary lines, whatever we draw. The middle section usually does cross. It crosses the horizontal. So we need the graphing calculator so we can plug in some more points. We got to do some evaluating. So let's type it in. Okay, when you type it in, it's probably easier to go back to the original. We only use this to get the vertical asymptotes. Other than that, I don't really need the factored version. In parentheses, x minus 1 divided by x squared minus x minus 6. And I'm going to press second graph, and I'm going to look at my table. Okay. It says to evaluate near the asymptote on each side. Let's start with 3, just because that's a positive number. What's a number that's very, very close to 3, but just a little smaller? Yeah?
Do you want a whole number or can it be a decimal?
I want a decimal that's extremely close to the number 3.
Then 2.9.
Even closer.
2.99.
Sure. We know we can't do 3 because that's an error. But let's do like 2.999. Very, very, very close to 3. What's happening to my y value as I get very close to the number 3? Where is it? Where's my y value heading? Yep. It's heading down. It's at negative 400. Right? So when I get very close to 3, but a little smaller, I am way down there. Now, we want to check what's happening on the other side of that asymptote, on the right side. So what's a number that's just a little bigger than 3? Yeah. Yes.
3.19.
You want to go closer than that.
Closer.
Yeah.
3.05.
Okay, yeah, I would even do like 3.001. Just go, go really close. The 3.05, that'd be okay.
Use the first thing that can be ran.
But now, when we're just after the number 3, my graph is up at 400. So it's going up after the number 3. So that's way up here. Now let's do the same thing for negative 2. What's a number that's really close to negative 2? Let's say a little smaller. So to the left of negative 2. Yep.
Negative 2.00 repeating 1.
Negative 2.001, sure. It's just a little smaller. And in fact, it just rounded it to negative 2. But when I'm at negative 2.0001, you can see what I typed in if I hover over it. I'm at negative 6,000. So just to the left of negative 2, I'm going way down. Without even doing it, what do you think is going to happen that's just to the right of negative 2? Where do you think my graph will be? Okay? It's going to go up. So pick a value a little bigger than negative 2, negative 1.9 now. So we're just plotting points. That's what we're doing. We're plotting points to get a good picture. Let me move these off my grid. And right now I've got 1, 2, 3, 4, 5 points. For me, that would be enough because I know what the pattern of this graph is going to look like. But if you're not sure, do a couple more points in this area and see what your graph looks like. Try like negative 1, 2, 3. Try negative 4. Just get another point. Negative 4, negative 0.35. So just below the axis. Negative 1, 2, 3, 4. 1, 2, 3, 4. Right about there. And as you keep heading to the left, you're just going to get closer and closer to the axis. So negative 10, now you're at negative 0.1. Even closer. So in the lower left, you're going to get a curve that looks something like this. It's going to stay really close. And it's going to curve down and go like that. Now in the upper right, you're going to get pretty much the same thing. You might want to try like 1, 2, 3. Maybe put a point in at 5 just to get one more point. 0.29. So just above. So 1, 2, 3, 4, 5. About there. And if you need more, you can do a couple more. But it's basically going to do this. Stay really close. Start to curve. And then get closer and closer that way. Okay, now the middle. You might, especially if it's your first time doing this, you might not be 100% sure what's happening in the middle. Well, it has to stay very close to that. And it also has to stay very close to that. But those two have to connect in the middle. So if you're not sure, try plugging in another point maybe when x is 1. 1, 0. Okay, that's a good one. If you're still not sure, do 2. 2, negative 0.25. Okay, now I got 3 points in that middle section, so I can kind of see the shape of the curve in the middle. It's going to do something like this. It's going to come down. It's going to start to curve. And go just like that. And that's what that graph looks like. So once you get your dotted lines, you can use the calculator to get as many points as you need so you get a good sketch. Okay, let's see how we did. So there's the lower left. There's the middle. All right, mine's not really perfect. It looks a little flatter in the middle than I had, but I mean that you're doing it by hand, right? So that's good enough. That's a good sketch. Any question on that? I had one more of those, and that was it. Let's see. Okay, we did one where the exponent in the top was smaller. That was a 1, and the bottom was a 2. Let's finish up with one where they're the same. Okay, what's the first thing that I always suggest you do to the bottom? Leave the top the same. What did I suggest on the last problem you do with the bottom? Yeah? Factor it. This is a little simpler factoring. This is not the 2 sets of parentheses because you only have 2 terms. All you can do there is pull out what they both have in common. Does anyone see what these both have in common? Yeah?
2x.
Well, yeah, we just can do an x.
Yeah, because 2 doesn't divide, goes into 5, right?
Right, if this was a 6, then I would say we could do a 2x.
Okay.
And that's going to leave you with 2x minus 5. So this is going to have 2 vertical asymptotes again. There's a number you can fill in here to get 0, and a number there. All right, let's write them down. Let's call this factor number 1, factor number 2. What number could I fill in for factor number 1, and it would make the bottom 0? Yeah?
Be 0.
0. What number could I fill in for factor number 2, and it would make the bottom 0? If you're not sure, off to the side, you can set this up and solve that for x, and that'll give you your answer. Max? 2.5. Okay, so we've got those. Another thing that's important is the horizontal asymptote. But to do that, I need the EBM first. What's the highest degree term in the top?
3x squared.
Highest degree term in the bottom? Yep. 2x squared. So I get 3 over 2 for my EBM. So now, what happens to 3 over 2 as x gets bigger and bigger? It stays the same because there is no x. So what's my horizontal asymptote? Yep. 3 over 2 or 1.5. I just do it as a decimal. That's easier for me to think about when I want to graph it. So when these exponents are the same, you will get a horizontal, but it will not be at 0. It'll be at a number above or below 0. What number? Well, that number. Yeah.
If you're, sorry, I'm just backtracking a little bit. If your horizontal asymptote, if you did have an x in that was approaching infinity, how would that change the horizontal asymptote?
If it was in the bottom, it would make the horizontal asymptote 0.
Okay.
Anytime there's an x in the bottom, it's always 0.
And if the x
We didn't do one with the x in the top.
okay, so we don't have to worry about that.
Nope, you're either going to have 1 in the bottom or you're not going to have 1 at all. Those are the two cases we would. All right, so now we're ready to sketch it, and then we just need to plot some points. So sketch your dotted line, so you have all your boundaries. 0 and 2.5. At least make it a little easier for me to sketch. So 0, 2.5. And where was the horizontal? 1.5. There you go. So now we got our boundaries. We need to type it in on the calculator and use the table now to get some points. How many? Usually 7 or 8 points is enough. I think that's about what we did in the last one. Okay, so we've got, in parentheses, that's important, just for order of operations. 3x squared plus x minus 4 divided by 2x squared minus 5x. Second table. Okay, let's start with some points near the vertical asymptotes to figure out if it's curving up or down. Okay, first vertical asymptote is at 0. What's a number a little smaller than 0, but very close? Yeah?
Negative 0.001.
Perfect. Okay, I can see what's happening there. What's a number that's close to 0, but now I want a little bigger? Mark?
Negative 0.009 or 0.9.
So we got one that's already negative.
Oh, so just 0.9.
Go closer than that. When I say close, I mean within like 100.
Like 0.929.
So I'd do 0.001. Because if you do you could do 0.9, but we're not really sure because that just says 0.23. But if you do like 0.0001, well, that's at 8,000. So I have no question now which way it's going. All right, now let's do 2.5. What's a number that's a little bit smaller than 2.5? Yep.
2.499.
Yep. And we're at negative 35,000, so I would say that's going down. And a little bigger, 2.5001. We're at positive 34,000. So we've got some good points on each side of the asymptotes. So just to the left of 0, you want to go way down. To the right of 0, way up. To the left of 2.5, way down. To the right of 2.5, way up. I mean, I know I can't graph a point at 34,000. My graph paper is not that big. The point is, it's up, way up. And just throw in a couple more points. I would do maybe like 1, 1, 0. That's a good point. So I kind of got the middle. Middle looks like this. It's a very slight curve, not as much of a curve as the last one. Because the curve is so slight, I think the calculator is going to have trouble drawing that. It's too steep for the calculator. It's probably going to give up drawing it. On the right section, let's pick a point maybe around 3. So 3, actually let's do 4. 4, 4, that's a good one. 1, 2, 3, 4, 1, 2, 3, 4. Okay, good enough. Just have it curve down. And let's get one more point over here. Oh, maybe negative 4. Negative 4. Let's see. 0.7. Well, just under 1. 1, 2, 3, 4. Right about there, but that's good. I can see it curving closer. All right, let's sketch it, but I really think the calculator is going to have a problem with the middle piece. I don't think it's going to do it right. What happened is it got too steep for it, so the calculator basically, it even had trouble with the left piece. It just kind of drew it, and it looked like it just stopped, but that's not right. It should keep going down, and it should keep going up. So that's a better sketch. And that's how you sketch a rational function. All right, so let's take a look at the homework. All right. 5. So at this part, let's make this 19. Comma 25. And yeah, I think that's good. So I changed about 3 or 4 of them. Okay, so that's the homework for tonight on 234. And we'll take a look at that tomorrow.